How do we identify bipedal locomotion from human fossils? Imagine walking through a museum filled with ancient bones and wondering how scientists figure out if these early humans moved on to legs. It's like solving a puzzle with clues from bones alone. Paleoanthropologists use specific features in fossils to tell if someone walked upright. Since soft tissues like muscles and tendons don't fossilize, they focus on bones to understand how these ancestors moved. They compare these bones to those of living primates to see what's similar and what's different. The key is looking at skeletal features that change when a species starts walking on two legs. The first big clue is the foramen magnum, the hole at the base of the skull where the spinal cord passes through. In four-legged primates, this opening is toward the back of the skull. In upright walkers, it shifts to a more forward position, aligning the head directly over the spine. This change helps support an upright posture. The pelvis also shows signs of adaptation. In bipeds, it becomes shorter and wider to support the weight of the upper body and keep the legs beneath the trunk. The hip joint expands to handle the forces of walking upright, and the thigh bone, or femur, angles inward toward the knee. This inward angle helps keep the legs close together, making walking more efficient. The lower leg bones tell us even more. The shin bone, or tibia, becomes thicker and more robust at the ankle to support standing and walking. The knee joint develops a distinct shape, with a concave surface that bears weight during each step. Fossils like the Kanapoi tibia from Kenya, which is about 4.2 million years old, show these features clearly. The foot is another important piece of the puzzle. Bipedal feet have an arch that helps absorb shock and a big toe that lines up with the other toes. This toe is no longer grasping like in tree-dwelling primates. Instead, it pushes off the ground during walking. The footprints at Laitoli in Tanzania, made around 3.7 million years ago, give us a real-life snapshot. These footprints show a heel strike, a push from the ball of the foot, and a big toe that stays in line with the others. The toe's slight separation from the others indicates it was adapted for walking rather than climbing trees. Early fossils like those of Ardipithecus ramidus, dating back about 4.5 million years, show a mix of traits. They had features for climbing trees but also signs of walking upright. This suggests they were facultative bipeds, meaning they sometimes walked onto legs and sometimes on four. Later species like Australopithecus afarensis, which lived between about 4 and 2.8 million years ago, show more consistent adaptations for upright walking. Their bones are more specialized, clearly indicating habitual bipedalism. Scientists also compare fossils to modern primates. Gibbons and siamangs, which sometimes walk upright in trees, help us understand what early bipedalism might have looked like. Chimpanzees and gorillas walk on their knuckles, while orangutans climb and swing through trees. By matching fossil features with these living models, researchers can guess how extinct species moved. Environmental changes also influence these adaptations. As forests gave way to open grasslands around 4.4 million years ago, walking on two legs became more advantageous. It allowed for long-distance travel and better visibility over tall grasses. Over time, species with more efficient bipedal features thrived in these new landscapes. In the end, identifying bipedalism from fossils involves looking at the shape and position of bones, especially the skull, pelvis, legs, and feet. Footprints add direct evidence, and comparing fossils with living primates helps fill in the picture. Combining all these clues helps us understand when and how our ancestors started walking upright.